In problem number 18, which of the following sets is not closed under division? To be closed means that when you perform an operation on two numbers that are in a set, you get a result that is also in the set. So for example, if we're working with natural numbers, when we add two natural numbers together, we get another natural number back. So we say that natural numbers, the set of natural numbers, is closed under addition. But the set of natural numbers is not closed under subtraction, because I could subtract two natural numbers and I get a negative answer. I could get a negative answer, and that is not a natural number. And so natural numbers are not closed under subtraction. So that's the basic idea here. Now, so the question, we're looking to find a set that is not closed under division. Now integers, for integers to be closed under a division, it means that I can divide any two integers and I always get an integer in response. But I know that that's not true, because if I divide the integer -1 by the integer 3, I get a result back that is not an integer. I get a result that is a rational number, or that is a real number, but it's not an integer. And so that's going to be the answer to this. Integers are not closed under division. Rational numbers, excluding 0 of course, are closed under division, because if I take, and again I'm only giving examples here, I cannot prove something by giving even an infinite, or I couldn't give an infinite number of examples, but I would have to give an infinite number of examples to prove that something is true. I only need to give one counterexample to show that something is not true. So I'm giving an example here to show that that rational numbers are closed under division, but this in itself is not a proof. So if I started with the fraction 2/3 divided by 4/5, my numerator is a rational number, my denominator is a rational number, and I divide them by inverting the denominator and multiplying, and so I get 10/12 or 5/6, which is also a rational number. Now I could probably do a proof in abstract terms with A, B, C, D and show that I'm always going to get a rational number out of this. So rational numbers are closed under division, but that's not what I'm looking for here. The same thing is true with real numbers. If I divide any two real numbers, excluding 0 of course, I'm going to get a result back that is also a real number. So we can't say that real numbers are not closed under division. They are. And the same thing is true with complex numbers. Assuming that we're not working with 0, any complex number divided by another complex number will also result in a complex number. Complex numbers have the form a plus bi, where a is a real number and bi constitutes, b times I constitutes an imaginary number, where I is the square root of -1. So if I were to construct a complex number, 3 plus 2i, and divide that by 4 minus 5i, the way I would simplify this is by multiplying the numerator and denominator by the conjugate of the denominator. And when I multiply that out using what we would call FOIL in algebra, I would get something like this: 12 plus 15i plus 8i plus 10i squared divided by 16 plus 20i minus 20i minus 25i squared. When I simplify that down, I'll get 12 plus 23i plus 10i squared divided by 16 minus 25i squared. But I squared is -1. And so when I substitute -1 for I squared, I'm going to get 12 plus 23i minus 10, which is the same as 2 plus 23i over 41. And if I divide each term in the numerator by 41, I get 2 over 41 plus 23 over 41 times I, which is in the form a plus bi, and so I have another complex number. So complex numbers are closed under division.